Hi again. If you watched the last lecture, that's super janky because I'm getting over being ill and it will now live on the internet forever. Welcome to the next lecture, Unit 8 in Statistics for Psychological Science Majors, where this one will also be janky and live on the internet forever. But I will lecture through Unit 8 for you. So let me share my screen and let's chat about section Unit 8. And let me move all my little Zoom menus around because they're in the way again. All right. So what about confidence intervals for t-test designs? Remember that we can estimate a 95% confidence interval for an unknown population mean, which we call mu, by using the sample mean and the population standard deviation, right? We had x bar plus or minus 1.96 times the standard deviation divided by the square root of it. X bar plus or minus 1.96 times standard error, right? So we did that. But what if we don't have standard deviation? Could we use our sigma hat? Could we use our estimated standard deviation? Yes, but kind of. We have to adjust the 1.96 because 1.96 is used for a normal distribution. In a normal distribution, right, a normal bell curve, right, 95% of the sample means fall between negative 1.96 SE and 1.96 SE. And this assumes the standard deviation is known, right? We know what that is. It's a standard deviation on a standard normal bell curve. But if we're estimating standard deviation with standard deviation with our hat on top of it, we get a t-distribution for the sample means. Recall that the shape of a t-distribution depends on the size of the sample, so it's not always a normal standard distribution. The shape can change. So if the shape can change, well, that means the data that's kind of left in the tails isn't always going to be 1.96. So in light of this, we have to define a generalized confidence interval where the value of t asterisk df depends on sample size. We're going to define as the value of t, which leaves 5% of the distribution in the two tails combined. So we're going to say 2.5 is on one side and 2.5 is on one side, 5% is on one side, 5% is on the other side and a different one, right? But combined, no matter how it breaks down, we're saying that 5% of the distribution, right, our standard little bell curve, we're saying 5% of that is left in the two tails. Sometimes we call this the critical value. You would see that referred to as CV, or the t distribution. Sometimes we call it t-crit, the critical value of the t distribution. But luckily, our SciStat calculator can find it. So here's what the formula looks like. We have x bar plus or minus this estimated t degrees of freedom times SE. So remember that our formula for standard error depends on the design. For a single sample or repeated measures designs, we have standard error equals sigma divided by square root of n. But if we had an independent sample, we have standard error equals sigma hat p divided by 1 over mu 1 plus 1 over mu 2, square root of that. So you need to know which one you're looking at, right? Are you looking at a single sample or repeated measures where the same participants were given the same conditions, right? They did this and then they did this, and we compared those scores, or is it independent samples where we have an experimental group and a control group, and we have different groups, different data, different numbers, and we're trying to find the t-test that way. We score it that way. So let's see, for example, one, a single sample design. One sample of 25 people is given a treatment. After the treatment, we find that x bar equals 22.2 with sum of squares of 384. So if you wanted to construct a 95% confidence interval for mu, the population mean of the treatment group, it would be the degrees of freedom is 24. So from SciStat, we find, let's see one more. Okay. From SciStat, we find the t asterisk 24 equals 2.06. So for a single sample here, we have SE equals sigma hat divided by square root of n. So sigma hat equals SS divided by mu minus 1, which gives us 384 over 25 minus 1, which gets us all the way down to 4. So for standard error, now that we have sigma hat, we can put in 4 divided by the square root of mu, which equals 4 over 5. So that gives us 0.08. So we put this all together, we have a 95% confidence interval that X bar is plus or minus T asterisk DF times SE, which looks like it's somewhere in the range between 20.55 and 23.85. We're 95% confidence that our population mean is within that 3-point, give or take, interval right here. What if it was an independent group design? What if we didn't just have one population that had the experiment, right? We had two different groups. We had our experimental group and our control group. So for independent group designs, the goal is to estimate the mean difference, right? Mu1 minus mu2. And the resulting formula for this 95% confidence interval looks like this. So we have mu1 minus mu2 in parentheses plus or minus T asterisk DF times SE. So look at this, or have our standard error where sigma hat for the population is divided by where is times the square root of 1 divided by mu1 plus 1 divided by mu2. So we need all of these numbers. So let's give this an example, some words here. Does watching educational TV as a kid predict better high school grades? So this group of kids over here of n equals 10. So we had 10 kids over here that watched educational TV. They had a mean of 93 and a sum of squares of 200. These kids over here did not get to watch educational TV. They had 10 people in this, 10 kids. They have a mean of 85 and a sum of squares of 160. So this mean difference of 85 and 93, is that significant? Or what's the 95% confidence interval for that? So for the mean difference, mu1 minus mu2, here's our formula. So degrees of freedom 1 plus degrees of freedom 2 equals 9 plus 9, which equals 18, right? It's not 10 plus 10 because degrees of freedom is number minus 1. So according to SciStat, we get 2.10. So then when we put it into this formula, our standard error formula, we get 4.47. So now we can know for a standard error 4.47, this is our number, right? 1 divided by 10 plus 1 divided by 10. Let me go back. Okay, so this is N1 and N2 is 10. This is not mu down here. This is standard error equals sigma hat P times the square root of 1 divided by N1 plus 1 divided by N2. So that's the number. So we have 10. 1 divided by 10 plus 1 divided by 10 equals 2. So when we put everything together, we have X bar 1 minus X bar 2 plus or minus this T asterisk degrees of freedom times standard error, which gives us a 95% confidence interval of 3.8 to 2 to 12.2. It seems like a pretty big interval to me, right? 3 to 12, that's like 9 points, give or take, that our interval consists of. So that's interesting that we can say, well, we're 95% confident that it's between 3.8 and 12.2. So hang in there. I know that was a big formula, and I'm sorry for, let me go back a few minutes just to clarify that this is N1 and N2, not mu. I know that I made a mistake on that a couple of slides ago, and I'm sorry that N's and mu's look so similar, but this is N. Let me see what else I said. Let's see, this is a sample of 25 people. So this is also N. This is N minus 1, so that's degrees of freedom there, 25 minus 1. Let me see if I said mu anywhere else I shouldn't have. So for this, the SE equals, this is N1 and this is N2, not mu. I don't know if I did that anywhere else. Okay, I think that's the only place. I've corrected it now, so hopefully I don't get a bunch of emails. Sorry about that, but that is what lecture 8 is about, getting confidence intervals for t-test. So I hope that is clearer than mud, and you'll reach out if you have any other questions.